I mean, you wouldn't have all this mathematics and nice methods of making gears if you didn't know how to draw all these different curves in order to make things work without any systems. I teach physics, and you know, if you're teaching introductory physics, it's very interesting to tell students, you know, how things interact and they become important. Even if at the time people were arguing about whether the Earth went around the Sun or the Sun went around the Earth, you know, a stupid question, because they both go around each other. And how it comes down to where it's very practical in the end. In fact, one of the things I worked on way back when I was a student was we got a germanium chip from AT&T and went and put it in an accelerator experiment, and we were able to detect incoming particles just by a little pulse that they made in this chip. The chip didn't work very well. The conclusion of the experiment was that solid state devices were so impractical because they broke down all the time. And you could, you know, they would spark, and you couldn't rely on them. That solid state devices would never be used. They were just a good toy. Even though we were probably the first person to ever use a solid state device in a practical sense. It was practical in the fact that we made it work, and we were able to count, you know, charged particles going through this little germanium chip, but it was not as, it was harder to do than doing it with some kind of crystal in a photomultiplier tube. But it did work.
Where did your research go from there? I'm just curious. I've never really had much of an understanding of the. I know that a lot of your life has been that of a teacher, but a much greater part of your life has been that of a researcher. What kind of research have you been involved in? Could you describe it?
Well, the important thing at that time of my life was the discovery of isobaric analog states. I mean, and
that's what you did over in Germany, right?
No, that's mainly when I did that in Germany, but that was, the discovery was made at Florida State University. And basically you think of we normally think of nuclei as being made up of neutrons and protons.
Okay.
And neutrons and protons have spin. But you can also think that a neutron and a proton is the same particle, and it's either a proton or a neutron, and that's called isospin. So if you just look at things like giant resonances, you would say, here's the protons, and here's the neutrons, and it's all one big soup, and the neutrons and protons are vibrating against each other, and you get some kind of a giant resonance. You can also think about single particle states, where you have a proton going around the outside of a nucleus, and you have a neutron going around the outside of a nucleus, so you have some particular state. Because one of them is a proton and one's a neutron, it's going to be in a different nuclei, but it's the same nuclear state.
Okay.
And that's what we basically found. All these states and other nuclei that are built and identical to states in what we call the Parrot nuclei. So we're able to classify hundreds of states and nuclei and make good sense out of it all. And you can look at how some of them decay and figure out what the nuclear structure of those states are.
So is that what you were doing at the Max Planck Institute?
And we were doing further studies of isobaric analog states in Germany.
And what have you been doing more recently, research-wise?
Well, I went to Los Alamos, and we were doing meson physics, where we were scattering pions off of nuclei. And that's pretty exciting. We saw all kinds of different states in nuclei that are excited by pi plus and pi minus mesons, exciting nuclear structure, and you know what's exciting about in physics are things that are simple.
Oh, really?
And most of the things that we did at nuclei at Los Alamos are not all that simple, like
Really?
isobaric analog states are. And so it makes it a little bit complex to explain this to you. Let me go to a different aspect of things. So while I was in Los Alamos, one of the ideas that we had was taking, there's a nuclear test ban treaty, and we have to get rid of a lot of our nuclear weapons.
Uh-huh.
So how do you, if you have, I don't know, 20,000 nuclear weapons, and your treaty only allows you to have 600 of them, then hopefully you want to throw away a whole bunch of them. So how do you decide which ones to throw away? Well, just like you take people like Patrick, who's a psychiatrist, and you want to find out whether they have good heads or not, you go do a CAT scan on their head, and you see if their brain is working okay.
All
Well,
right.
you can't really do a CAT scan on a nuclear bomb because there's so much metal in there that the X-rays don't penetrate. But you can do a CAT scan instead of using X-rays. You can do it with a high-energy proton beam. So we did CAT scans. Well, since I'm at a university, you don't have much of a clearance. So we developed a technique for doing CAT scans on nuclear weapons. And I assume that they are doing that in order to decide which nuclear devices to throw away and which ones are to be kept. But the same technique can even be used in a much more interesting way.
Uh-huh.
For example, you can take a gasoline engine in a Ford automobile car and do the same instantaneous CAT scan, and you get about 6 pictures of the inside of a cylinder as the spark plug sparks and the explosion pushes down the cylinder. And you can see if that explosion is uniform, if the pressure wave is hitting the top of the cylinder, and if you get the maximum amount of energy out of this engine by the way you design the cylinder and the spark plug and the top of the cylinder. So it has a tremendous amounts of applications, even if you're not very interested in the weapons development.
Weapons. What about this thing? I mean, weren't you doing something where you were smashing things into each other, nuclear?
The present research that we're working on is what's called relativistic heavy ion physics.
Relativistic?
Relativist, yes. You see, nuclei.
Okay.
Nuclei are basically spheres.
All right.
Okay, and then special relativity, you can say if something's going almost at the speed of light in that direction, then it gets shortened. That's called length contraction.
Okay.
So now you take a sphere, like a nucleus,
Okay.
and you make it travel almost at the speed of light. It goes along, and as it becomes a pancake. So you have an accelerator circular, or almost circular, and you send a beam into it, and it goes around one way, and you send a beam in it, and it goes around the other way, and you focus the 2 beams together here, and they collide. So what does that mean? That means that you're taking 2 of these pancakes that are going at 99.4% the speed of light, and they collide with one another. They have so much energy. Now these are nuclei. If you were traveling with the nucleus, you would see a sphere. In the lab system, you see a pancake. Those 2 pancakes go together. They have so much energy, they go right through each other.
Wow.
So now